So this is chapter 3 and the additional information that the calculus-based students need to know. So in algebra-based physics, we typically talk about a velocity vector, and we break it up into two components. We break it up into an x component and a y component. So let's say this is a velocity, and this is v sub x, which is the x component. And the y direction is this, so this is v sub y. And so we break it up into, we said the x component of velocity is just the hypotenuse of the right triangle, which is v times the cosine of the angle theta, which is the angle between the horizontal and the actual velocity. And v sub y is equal to v times the sine of theta. So we kind of keep the x and y directions separated in all our discussions. The only thing that connects the two is time. Now what we do in calculus-based physics is we talk about the three dimensions of x, y, and z. So here we go, x, y, and z. So this is the x direction, this is y direction, this is z direction. And our position vector, which is from the origin to some point in space. So this is my point in space. And it has coordinates. So my r, and this is a vector, my r vector, you can represent it as three terms, which would be your x, y, and z coordinates. So let's see, it's 2, 3, 3. So you go 2 units in the x direction, you go positive 3 units in the y direction, and then you go positive 3 units in the z direction. So that's one way of representing this position vector. Now there are what we call unit vectors that are vectors that go along the, well, unit position vectors, and these are in three directions, in the three principal directions. So we have what we call I hat. So it's I with a little hat over top of it. That is a unit vector in the x direction. Unit means that it has a magnitude of 1. So maybe 1 meter, if we're talking about the metric system. The j hat would be the unit vector in the y direction. And k hat is the unit vector in the z direction. So these are vectors. So this is it has a length of 1 pointing in the positive x direction. The j hat vector has a length of 1 in the y direction, and the k hat vector is positive 1 unit in the z direction. So those are called unit vectors. And so our position vector can consist of three parts. It consists of the magnitude of the position in the x direction plus the magnitude of the position in the y direction times j hat, and the magnitude in the z direction times k hat. So this is a scalar multiplied by a vector, and that gives you a vector. And these are the magnitudes. So for our particular case over here, rather than writing it in these little brackets that are like small triangles with the side missing, we would write it as 2I hat plus 3J hat plus 3 k hat. So these two things are basically saying the same thing. Here we're giving the coordinates in the x, y, and z direction, and here we're doing the same thing, but we're being more explicit about the vector nature. Okay, I'm just checking to see if I was recording, which I am. Good. Okay. So you can also have it where the position vector, rather than just, this is just a given one position vector, but you could have it as a function of time. So you might have 3t times I plus 4t squared times j plus 5k. And so this is a parametric equation because the parameter is t, and you know, start at t equals 0, and then if you want to know the position at any point in time, at any positive value of time, you just plug the value in, and then you'll end up with the exact position vector at that particular time, and that'll be your position in three-dimensional space. So let's say if I were given, I have, you know, if I want to say the position is at the position, location of the object is at 50 degrees relative to the horizontal. We're just going to do this in 2 dimensions right now. With a magnitude of 5 meters. So what does that mean? Well, if we were to draw a coordinate system, here's an x direction, here's a y direction, so we're just doing 2 dimensions. We would have this position vector which would start at the origin and point from the origin to the point in space, and 50 degrees is like that. And so the magnitude of this vector is 5 meters from the origin. And the orientation theta is 50 degrees. So how would we rewrite that in terms of this position vector notation? Well, you do the same thing. You break it up into a right triangle. So you have a horizontal component in the x direction. You have a vertical component in the y direction. And so we would say that the magnitude of the position for the x direction would be equal to the magnitude of the vector. So let's put a little vector there. The magnitude of the vector, which is 5 meters, times the sine of 50 degrees. So let's say that's 5 meters times the sine 50 degrees. Let's get my calculator. Five times the sine of 50. And you get 3.83. So the x component of the position vector is 3.83 meters. Likewise, the y position vector, the y component is the magnitude of the r vector, which is the length times, actually this was r sub y, sorry, because it's the sine. So that's r sub y, r sub x is the cosine of the angle. So we have 5 meters times the cosine of 50 degrees. Five times the cosine of 50 is 3.21. 3.21 meters. So in our notation, we would say that the position vector, which gives us both magnitude and direction, is going to be 3.21 I hat plus 3.83 j hat. So rather than describing the position vector in this way of relative to the horizontal axis and the total magnitude, we can break it up into the two components, which we specify using the unit vector. So I know that to get to my final point, I go 3.21 units in the x direction, and I go 3.83 units in the y direction, and that resultant displacement or position is the same as if I drew a straight line from the origin to this point at an angle of 50 degrees with a length of 5. And if you take this square plus that square and take the square root, you'll get 5. So that is unit vectors. Now, in terms of the things that we deal with, displacement, velocity, and acceleration, how do we represent that using this format? So our delta, before we've dealt with delta x in one dimension. And in two dimensions we would talk about delta x and delta y. From a calculus-based physics standpoint, we would say that the delta r vector is equal to the final position vector minus the initial position vector. So let's say our initial vector, we'll just do 2 dimensions, but 3 dimensions are just the same. So that's my initial position vector, 3 units in the x direction, 4 units in the y direction. And let's say I go to 5i plus 7j. So that's my position vector finally. So let's just draw that, see what that might look like. So we would do our coordinate axis, and we would do the first vector, which would be, so we go 3 and then up 4, which would be about there. So that would be our initial vector. And then the final vector would be 5 and 7, which would be up here somewhere. So we'll call that our final. Delta r would be this vector. So that when we take the initial vector and we add the change in vector, we get our final, or delta r is our final minus our initial. So you can rewrite that as saying that our final vector is equal to the initial vector plus the change in position vector. Either way would be right. So it's just simple algebra, but what we do is we keep it within the components. So our delta r vector is going to be equal to the final, so this is the final. So you'll take 5i hat plus 7j hat, and you'll subtract the initial like that. So you take 5 minus 3 is 2, so you get 2i. 7 minus 4 is 3. So you get plus 3j. And if I were to take this delta vector here and put it back to the origin, it would be plus 2 and then plus 3. You know, right here it's out in space, the delta r vector. Another way of thinking about it is if you take the parallelogram that's formed by this one being one side and this being the other side, the vector that goes through the diagonal would be that vector, which would give you the resultant vector. So this is the displacement vector. You take the change in the position vector. What we did in one-dimensional motion was we said final position x sub final minus initial position x sub initial. And it was just, they were numbers because we were only going one direction. But when you're in 2 dimensions, you have to take into account that your changes are going to be in 2 dimensions. Again, it may not appear this way, but the origin is completely arbitrary when you're talking about changes in position, which is displacement. The change in position is irrespective of where you define your coordinate system. R sub f and R sub I are going to be dependent upon the origin, but the change is going to not be dependent upon that. So let's just say I move my coordinate system over here, and so my position vector would now be from here to there, and from there to there, but my delta R would still be the same thing. So it doesn't matter how far your position is away from the origin. What we're interested in is the change in position, the displacement. And that's irrespective of where the origin is. So likewise, when we get to defining the velocity vector, there's 2 things. It's going to be the dr vector dt. So we take the derivative of the r vector with respect to time, and that's going to end up with a basically what you're going to end up with is an r sub x times I plus r sub y times j, and both of those you're going to take the derivative with respect to time. You do them individually because you're adding 2 terms, and if the sum of the derivative, the sums of sum of derivatives, that's the I forget the exact name. It's probably sum and difference rule. So what you get is you'll find that the velocity is dr sub x dt times the unit vector I plus dr sub y dt times the unit vector j. So you take the derivative, whatever this function is a function of the function of time. R sub x is a function of time, R sub y is a function of time. You take the derivative separately, and likewise you can then break your velocity up into a v sub x, which is dr sub x dt, and a v sub y, which is dr sub y dt, times the corresponding unit vectors. And then you can do the same thing for acceleration. So the acceleration vector is the derivative of the velocity vector with respect to time. You can break the velocity, you've got it broken up there according to direction. So that would be v sub x times I plus v sub y times j. And again, you can do each of those separately. That's what the principle of superposition basically says. You can, the sum of the derivatives is the derivative of the sum. So we would get dv sub x dt times I plus dv sub y dt times j. And so the acceleration vector, you can have an a sub x times I plus a sub y times j. So that's how we handle things in calculus. And we can represent these as a function of time, and then we can take the derivatives with respect to time. So that's the calculus part of the whole thing. So what I'm going to do is just work a couple of problems I want you to watch separately to help you understand what's going on here.